This is lecture number 20. What we're talking about today is basically two topics that are related to each other. We want to understand shapes of graphs of functions, and more specifically, what the derivative tells us about those shapes. So we want to understand how to find places where the graph is increasing or decreasing, and places where it is concave up or down, and also where that changes, which is called inflection point. And there's going to be two derivative tests, first and second, that allow you to classify uh, critical points as minimum or maximum. That's the goal for today. So this box just says everything that I just said. All right. So first of all, we have to start with definitions. We're going to define the words increasing and decreasing. And usually we're going to be talking only about intervals. It might be possible that we talk about functions defined on like pieces of intervals, separate intervals, and then we're talking specifically about each one of them separately. So a function is a function defined on an interval is called increasing when basically when the graph goes up, decreasing when the graph goes down. But mathematically you say it like this: increasing. F of x is always less than f of z if you take points x less than z in this domain I. So that would be the first picture here. If you take any 2 points x and z with x less than z, you find that the value of f of x is less than that of z. And for the second point, second picture, what changes is for example, the first one right here, the f of x has to be larger than f of z if x is smaller. So that would be this. So this is what increasing and decreasing means. It applies to basically any function. But if the function is differentiable, we can talk about this in terms of the derivative, because essentially the derivative is the slope of the tangent line. And if you think about slopes of tangent lines to the first graph here, which is increasing, you see that they're all positive. And in the second one, they're all negative. So this is a theorem that you can prove, and you have to if you take an analysis course in the future. But for us, we're going to accept this as intuitively clear. This is called the test for intervals of increase and decrease. So it works like this. If you have a function that is differentiable on some open interval I, if the derivative is always positive in that interval, then the function is increasing there. And similarly, if the derivative is always negative, then it is decreasing. So a result like this allows you to quickly find what's called the intervals of increase and decrease of a function, which just means, find the locations where this function is increasing and decreasing. So that's the problem here. It's a very simple one. I give you a function. It's a cubic polynomial. Determine the intervals of increase and decrease. So we all know the cubic polynomials usually look like this, or maybe like this. They can have these two critical points. Sometimes they don't. Sometimes it's like entirely decreasing or increasing. But using the derivative now, we're able to quickly find out, like let's say the graph is the first one, we're going to be able to quickly find out these locations right here where it was increasing first and now it's decreasing and then it's increasing again. This is what we're trying to describe here. The derivative is going to allow us to do that. So let's see how. Well, take the derivative. That's going to be 6x squared minus 6x minus 12. According to the result up there, we just need to understand where the derivative is positive or negative. And that's going to give us the intervals of increase and decrease. So we need to understand this function here, where it is going to be positive or negative. The best way to do this is, first of all, find the places where it is 0. So find dividing by 6 now in order to solve the equation f prime of x equals 0. The 12 becomes 2, for example, by dividing by 6. You can factor this one as, let's see, minus 2 plus 1. So the two roots of the derivative are the numbers 2 and -1. What we want to understand now is actually where this derivative is positive or negative. So it's going to be in between these guys. It's going to have either a positive or a negative sign. So you can do this to be sure. The 2 points divide the real line into 3 separate intervals. There's the interval before the number -1. There's that between -1 and 2. And there's from 2 onwards. F prime is going to have either a plus or a minus sign in each one of these pieces. A way that you can find out is by plugging in points from each piece into the formula for F prime. So for example, F prime, let's say -2 is a point in the first interval. F prime of -2 is, look back into the formula for F prime. So you have 6 times +4 minus 6 times -2 and -12. So it's positive. This is 24, but what we care about is that it's positive. So you can draw a plus sign here for F prime. I'm drawing F prime in this table. So you do this for the other ones as well. Like 0 is a point in the second interval. F prime of 0 is -12, negative. And then 3 is a point in the last interval. F prime of 3 will be 6 times 9 minus 6 times 3 minus 12, whatever this number is, definitely positive. You know, that it's not always the case that it keeps changing sign like this. If you found a plus here, it's definitely minus and then plus and then minus again if it changes again. That's not true always. Usually it is, but it's possible like that this is a plus and this one is also a plus. So you have to really test each one separately. But we have the signs of F prime on each interval. Those are going to give you the intervals of increase and decrease. So we can say that now this relates back to the original function. If F prime is positive, then F is increasing. F is increasing on the intervals -infinity to -1, and so you use a union sign. I mean, or is the meaning of union sign. It's increasing here or also here. So from 2 to infinity, and then F is decreasing in the other interval, -1 to 2. You might also write these with closed brackets instead of parentheses, instead of open parentheses. That's really not important. Getting the intervals correctly is what we care about here. Whether or not you include the endpoints is a matter of convention. We're not going to include them. But this is what the problem was asking us to do. So I'm going to move on. Kind of a different problem here. Sketch the graph. Sketch the graph of a function with a domain between 0 and 10 with these 4 properties. So we're going to draw all of that. I mean, first of all, we are going to draw a little sketch. It goes between 0 and 10. The function must be differentiable at all points except 3. So not differentiable at 3. The derivative is negative between 0 and 3. So the function goes down, decreasing. And also between 8 and 10. So like this, decreasing. Now the derivative is positive between 3 and 8. So it is increasing here. And then f prime of 8 exists and it's a 0. So the function has a horizontal tangent line there. But the one at 3 does not exist. So at the point 3, we might create, I mean, we cannot create, well, we can create a discontinuity, or probably easier to do like a cusp, a sharp corner. So that's the scheme of what the function does. And now, but just by looking at it, you can come up with many possibilities. So the function, it does not have a value at 0. 0 is not included in the domain. It does have a value at 3. but it's not differentiable. So I'm going to do like a cusp, like this sharp corner. And then at the number 8, it has a horizontal tangent line until it goes down again, not having a value at 10. So yeah, this is a possible graph here. The way that I did it, it doesn't quite look like a cusp here. If you think about it, you might think this is a smooth transition. So I'm going to erase this first part and do it again, making sure it's decreasing, but creates a sharp corner like that. This is much clearer now. That's your f function. All right. Here's an important remark about the test involving derivatives and increasing versus decreasing. The converse is not necessarily true. That is, it's possible for a function to be increasing even if f prime is not always positive. For example, f of x equals x cubed. Let's quickly find what f prime does. F prime is 3x squared. It is actually larger than or equal to 0 always. It is strictly larger when x is not 0, but it is actually equal to 0 at the number 0, right? If you plug in x equals 0 into the formula, you get f prime of 0 equals 0. So you see that the function itself, though, it is increasing. This is x cubed. This is what it looks like. It keeps increasing, even around the number 0. But the derivative there was not strictly positive. It was equal to 0. So be careful with what this test says, which I'm going to go back to so we can read that again. It is just saying that if the function has a positive derivative for all points in an interval, then you know for sure it is increasing. But it doesn't go the other way. It might still be increasing even if it's not always positive. The derivative is not always positive. It might be equal to 0 at some points. All right? So just always remember the x cubed function as a quick example of this. But let's move on. Connected to all this, there is now something called the first derivative test. This is a test that allows you to classify critical points as local max, local min, or neither by using the derivative. This is how it works. So you have a continuous function on a certain interval. It's supposed to be differentiable at all points, except possibly at a critical point A. So the function is defined there. F of A exists because it is continuous, but it is a critical point. So it might, f prime might be 0 there, or it might not exist because the function does not have to be differentiable there, but it could. Those are the hypotheses. Usually we don't really care about this. They're always going to be satisfied for our examples. But then what happens? What is the actual test? It's essentially looking at whether the derivative changes sign around this number A. So if the derivative is positive before A and negative after A, think about what that looks like. Positive before A, so increasing, and then there's the value at A, maybe it's the derivative is 0, then negative after A, so decreasing. What does it look like? The function has a local max. And then similarly for the other one, just change the behaviors. If the derivative is negative before and positive after, it must be a local min at that number A. Whereas if the derivative actually does not change sign, maybe it's positive and remains positive after, then A is actually not a local extreme point. And I have all of the examples drawn in here, different values of A. A1, A2, A4 are critical points because f prime is 0. A3 is also a critical point because f prime does not exist. It's a sharp corner. The other ones are all 0. But look at the behavior of f prime. F prime is positive before A1. The function is increasing. And then negative after, it's decreasing. So A1 must be a local max. As we can see from the graph. This is a a valley, sorry, not a valley, the peak of a mountain. The valley, it would be A2. A2, around that we have decreasing first, increasing after, so local min. Around A3, increasing first, decreasing later, so again, local max. And around A4, the function actually does not change behavior. The derivative is negative before and remains negative after, even though it became 0 at A4. So this is like the x cubed function. This point is not a local min or max because the function has larger and also smaller values around it. So a very simple test. I hope you find it easy to understand, easy to think about, because now we have a problem about it. Find the critical points of this function. Use the first derivative test to classify them as local max, local min, neither. So we have a piecewise function. The break is at the number 3. So let's try to, first of all, find the critical points. Those are the points where the derivative is 0 or does not exist, by definition. The only point that we see here where the derivative might not exist is the number 3. It's the break between the two functions. So let's analyze that one first. F prime of 3. When you have a piecewise function like that, F prime of 3, how do you find that? You need to use the definition like this. This is what a derivative actually is. Every time you calculate a derivative, this is what you're secretly doing, except that you actually do have to do this directly if you have a piecewise function because it has two separate definitions on either side. So you need to analyze this limit here. If it exists, then that's the derivative. If not, then the function is not differentiable. And in this case, you can see that it's not going to exist. If you come from the left, for example, yeah, let's do that. So if you are to the left side of the number 3, then the definition of f of x is the first expression, 12x minus x cubed. What is f of 3? F of 3, looking at the first expression, is 36 minus 27, so 9, divided by x minus 3. All right, this is a 0 over 0 limit. You can do whatever techniques you like to do for this one. But we can use L'Hopital here, definitely, because it's 0 over 0. Now we have that at our disposal. So doing that very quickly will lead you to 12 minus 3x squared divided by plus 1. And this limit is whatever it is. 12 minus 27, so minus 15. But if you do it from the right, the same expression, what changes now is f of x. The value of f of x on the right side of the number 3 is now given by the expression 12 minus x. So on the numerator, you have 3 minus x. Denominator is x minus 3. Those simplify, leave just a minus 1. These are different. So the f prime of 3 does not exist. That means 3 is a critical point. It would be a huge coincidence if it actually existed because we just pasted together two functions. What's happening is that they're not pasting smoothly. They're pasting at a sharp angle. So it creates a critical point there. Very good. So this is the critical point where the derivative does not exist. There might also be points where it is equal to 0. We have to check for those. So where is f prime equals 0? Looking at the first expression, 12x minus x cubed. So yeah, let's now find where is it equal to 0. If x is less than 3, if you're using the first expression, then you need the derivative of x cubed minus 12x equals 0. That was the expression, right? Sorry, it's the contrary of that. 12x minus x cubed equals 0. Okay, this derivative is 12 minus 3x squared. So x squared equals 4 after dividing by 3. X is plus or minus 2. Both of these numbers are less than 3. So they are candidates for, they are critical points. They are locations where the derivative is 0. Meanwhile, if x is more than 3, there's nothing to do. If x is more than 3, the function is given by 12 minus x. That's not going to have a 0 derivative ever. If you try to find this solution to this, minus 1 equals 0, there is no solution. Okay, so we finally found all the points where the function has critical points. It's -2, +2, and 3. Here the derivative is 0. Here the derivative is 0. And here it does not exist. Now, if you look back in the problem, they're saying use the first derivative test to classify these points as local max, local min, or neither. So we have to remember what the derivative test said. It says if f prime goes from plus to minus, then the point must be, imagine going from plus to minus, local max. So that's what it says. We have to understand the sign of f prime in each one of the pieces. So let's try to do that. But before -2, sorry, it's not going to fit here. Let me write it down here. Before -2, between -2 and 2, between 2 and 3, and after 3. What is the sign of f prime? All right, so what is f prime of, for example, -3, or any point in this first interval? Do we have an expression for f prime? Remember, the function has 2 pieces, but if you are in this first interval here, you're definitely using the first piece, x less than 3. You're using this expression here for f prime. So that's this one. F prime of -3 will be 12 minus 3 times 9, 27. So definitely negative. All right, the f prime is negative here. So we're going to do the same thing for all the intervals. A good point in the second interval would be 0. In this interval, you're still using the same expression for f prime. This expression is valid for x less than 3. So we're still using this one. F prime of 0 is 12, positive. Between 2 and 3, not much you can do there other than plug in the number 2.5, I guess. It is still the same expression. It's going to give you a negative number if you compute this. I mean, this part we should probably figure it out. It's a parabola. F prime is a parabola. We know what parabolas do when they change sign. This is the parabola that points down, right? So it's not surprising that it looks like this, minus, plus, minus. And then finally, after 3, for example, plug in f prime equals of the number 4. Now be careful. You have to use the other expression for f prime, this one. Because now you're after the breakpoint in the function. The function changed behavior after the number 3. This is the new derivative, -1. And f prime of 4, it is -1, it is negative. So also negative here. You see that what I just told you, even though it's 2 neighboring intervals, the signs of f prime can be the same. So now you're good to go. By looking at how the f prime is before and after each point, you can conclude that in this case, -2 is, so if f prime went from negative to positive, imagine what the function is doing. It was decreasing and then started increasing. So you probably want to draw this in here actually. Decreasing and then increasing, so local minimum point. Next, the number 2, increasing and then decreasing. 2 is local max point. And finally, around the number 3, decreasing and decreasing again. 3 is neither a local max or local min. That's the answer to the problem. So this is how the first derivative test works. You're looking at how the derivative sign changes before and after each critical point. Quick remark here before we move on to concavity and second derivatives. If you have a continuous function containing exactly one local extremum, then it must be also global. I mean, usually we don't use this fact, but it's useful to think about, I guess, for us to understand the concepts. Just think about this. You know that when you find a local extreme point, let's say a local min, that might not be a global min. For example, a function that looks like this. This is a local min right here, but it's not global because the function eventually goes back down in here. However, if it is exactly one local extreme, no others, then that must be a global. That's this picture here. Imagine this function. It has a local extreme here, the number a, but it is supposed to be the only one. So it's going to be impossible for it to turn back around and start going down again, because that would create another critical point, another local extreme. So when you have a function and you find just one local extreme, you immediately know that that's a global extreme. Honestly, not very useful. Checking if something is global or not is very easy anyway. That's the procedure where we compare all the possible candidates, right? So that's not, I would not say this is useful, but it is useful to understand. Just see that you understand what's going on. So for example, verify that the function x ln x has a global extreme value. Is it max or min? So first of all, the domain of this function is between 0 and infinity. 0 excluded because of the logarithm. Let's find the extreme values or local extreme values. Those can only be in the interior of the interval. They are locations where the derivative does not exist or is equal to 0. So let's find f prime. You need a product rule for that. I'm applying that very quickly. You have ln x plus 1. So critical points. Critical points. F prime always exists. This expression is well defined in the inside of the domain. So that's not an issue, but it might be equal to 0. And there's exactly one location where this is 0. X is e to the minus 1, or 1 over e. Only one critical point. And well, so 1 over e is the only local extreme. I mean, we don't know that it is extreme yet, so I should not say that. I should start by saying critical point. It is definitely critical point. The derivative is 0. But do we know if it is going to be a local min, local max? Well, we can use the derivative test, the first derivative test, to conclude that. So f prime of x, that's the expression ln x plus 1. Let's see what happens before and after this point. So plug in points before and after the number 1 over e. One over e is like, it's between 0 and 1. You'd have to plug in a very small x for the first interval, like f prime of 0.001, to check whether this is plus or minus. But you don't have to know the exact value for this. This should be easy to think about. Just remember that ln x approaches negative infinity as x approaches 0. So this is probably a very negative number, right? We don't know the exact value, but it is negative before. So just because I know what ln x looks like around the number 0, ln x goes down like this. So we don't actually have to plug in an exact number. However, for the other one, we do have a good number. The number 1 belongs to that other interval, and then f prime of 1 is ln of 1, 0 plus 1, so positive. So f prime is doing this, negative first, and then positive. This means that 1 over e is local minimal. And to connect this back to what we were just talking about, because it is the only one, it must also be global. 1 over e is a global minimum point. But I would say that the value in this example is really, once again, the first derivative test. All this business here. Finding the derivative, checking its sign around the critical points. But let's move on to other topics. This is now the second half of the lecture. We want to talk about concavity now. This is going to be connected to the second derivative, as we're going to see. So we've already talked about concavity when we were talking about linear approximation. We defined it as the shape smile versus frown. So a graph is concave up when it is a smile and concave down when it is a frown. But it might be like non-differentiable graphs also like that. Those are also classified as concave up and concave down. But if it is differentiable, if you have a differentiable function, it's possible to give a definition / theorem, whatever you want to call it, for concavity based on the whether the f prime, the slope, is increasing or decreasing. Here's how it goes. Let f be a differentiable function on a certain interval. If the derivative is increasing, so now we're not looking at whether the derivative is positive or negative, but rather increasing or decreasing. If the derivative is increasing, the function must be concave up. I'm going to go down to the example before we move to the next point so we can see this. Look around, before the number 2. So in this interval I here, the derivative, it is initially negative, then becomes positive, but that's irrelevant right now. What we're talking about is it is increasing. The derivative is a very negative number here, then it becomes a slightly less negative number, then it becomes very close to 0 and starts becoming positive and larger and larger. The derivative itself is increasing, and that's causing the graph to have this shape, a smile, so concave up. That's what we're talking about now. And then similarly, if the derivative is decreasing, that's going to cause a frown, so concave down. That's what's happening after the number 2. Look at what the derivative is doing. Initially very positive, then going to 0 and then decreasing, then becoming negative and more negative, right? So that's what happens. And then, by the way, what is an inflection point? That would be the point 2 here. It's where the concavity changes behavior. So a point A such that the function is concave up before it and down after, or vice versa. That's called an inflection point. So in this example, 1 and 3 are critical points of the function f. 2 is inflection. Because this was concave up and now it became concave down. Okay, but now we have a theorem. We have a connection to the second derivative. We've just discussed about how the derivative of a function tells you whether the function is increasing or decreasing. That was all the stuff in the previous half of the lecture. Now the function that we want to know whether it is increasing or not is the derivative, is f prime. If we take another derivative of that, so f double prime, let's say we find f double prime is positive, then that would mean f prime is increasing, so we are concave up. So that is now the connection here to this theorem. If you have a twice differentiable function on an interval, if the second derivative is positive for all points in that interval, then the function must be concave up. Second derivative negative means concave down. And if you have a point A such that the second derivative changes sign around it, let's say negative first, positive later, or vice versa, then it is inflection point because the concavity is changing behavior. So now we can relate geometric properties of the graph to the second derivative. Let's see a quick example. Identify all critical points and inflection points of cosine x. The domain is from 0 to 2 pi open. And then determine the intervals of increase, decrease, as well as the intervals where f is concave up or down. So cosine between 0 and pi and 2 pi, we should start taking derivatives, two derivatives, because we know we're going to need those. So that's very easy. So first of all, critical points. Critical points is where the derivative is 0 or d and e. Critical points. Well, this derivative always exists. It's always minus sine x, but it might be 0. Where is sine equal to 0? Very important. You don't include the endpoints of the domain. In this case, they're not even included in the domain itself. It's open at 0 and 2 pi. So inside here, there is only one place where sine is 0, and it's equals pi. That is your critical point. All right. Now, this is going to be enough for us to determine intervals of increase and decrease. But if we also want to determine concavity, concave up, concave down, we also need to understand where f double prime is positive or negative. So for concavity, need to know where f double prime is positive and negative. And this is once again the same procedure. You have the function f double prime minus cosine. So you can try to decide where it is 0 first, and then analyze separately the pieces that breaks the interval into. So minus cosine equals 0. In other words, cosine equals 0. Where does that happen? Think about your unit circle. Cosine is 0 at pi over 2 and 3 pi over 2. So in between these numbers, pi over 2 and 3 pi over 2, the function f double prime is changing sign. Meanwhile, around the number pi, the function f prime is changing sign. So let's keep those three numbers in our analysis. In other words, let us divide the whole domain into these four pieces created by the three numbers, pi over 2, pi, and 3 pi over 2. So like this. Four pieces. The pi is the critical point. The other ones, pi over 2 and 3 pi over 2, they are locations where the double derivative is 0. They might be inflection points. In fact, they will be. But what we want to know really is the sign of f prime and f double prime. So we're going to do this. Think about angles in each one of the quadrants. Look at the formulas for f prime and f double prime. They are sine and cosine, but with an extra minus in front. So in the first quadrant, they are both negative. In the second quadrant, what changes is the cosine. The double derivative becomes positive. And then after that, the sign changes, and then cosine again. So what I'm doing is just plugging in angles from each one of these pieces into the formulas for f prime and f double prime, which are up here. So this information right here gives you exactly what you need for intervals of increase, decrease, and intervals of concavity, which, going back to the problem, that's what they were asking for. So we can do that. Looking first at f prime, f is decreasing on 0 to pi. You could write this as a union of the two pieces, right? But that is just the interval between 0 and pi. If we include the number pi over 2, which we might as well. And then similarly, increasing in the second half. Increasing on between pi and 2 pi. And then f is concave up on, where is it concave up? So where is f double prime positive? You have these two pieces which are together. You can make them one piece between pi over 2 and 3 pi over 2. But concave down on. So now for f double prime negative, you have two separate pieces. You're going to use the union notation of those two intervals, the first and the fourth interval. This is the answer to the problem. And we can draw the function based on these. They did not ask us to do that, but might as well. Remember, the function was the cosine function. But we can see that this is exactly what we know the cosine function does. So look in the first interval right here. Well, first of all, the function should be decreasing in the first half and then increasing in the second. But in terms of concavity, it's up in the second and third piece and down in the first and fourth. So think about the cosine graph now. It does this. Sorry, it crosses here. Right, this is cosine of x, which is the f function. You can see that it's doing exactly what our prescription said. Like this is a frown right here, then it's a smile, then a frown again. And similarly for decreasing, increasing. All right, so enough of this example. The answer was up here, these 4 lines. I'm gonna just leave this as an exercise for you. It's very similar to what we just did, but kind of reverse engineered. You're now sketching the graph of a function. I'm gonna divide the domain into 4 pieces, and I'm prescribing the sign of the derivative and the second derivative in each. So one of them is gonna tell you if it's increasing, and the other is gonna tell you if it's a frown or a smile. Like the first one here, increasing and smile. So it must look like this. Then increasing and frown. This is what a frown looks like when it is increasing. And now we change to decreasing. Decreasing and frown. And then decreasing and smile. Like this. So try to piece those together, come up with the graph of a function. This is really not that difficult. Quick remark. So remember what inflection point is. Inflection point is a point where the behavior of concavity changes around it. Maybe concave up before and down after, or vice versa. Usually, for that to happen, usually you have f double prime of a equals 0, just like we had in the cosine function. So if f if you have a inflection point, let's say concave up before and then down after, usually for f double prime to change from positive to negative, it will have to be 0 at the point. What this remark is pointing out is that it's possible that it does not exist. So be careful with that. This example here for a equals 0, the function x to the 1/3, it looks like this. So it's a smile first and then a frown. So this is an inflection point. But if you try to compute f double prime at 0, you're going to see that it does not exist. Instead of being 0, it actually does not exist. So we're just pointing out this can happen. It does not have to be equal to 0. And another remark in a similar vein, sometimes you do have a point where the second derivative is 0, but it is not an inflection point. For example, x to the 4th. X to the 4th looks like a parabola. It is a smile before and also a smile after. This is not inflection point because the concavity is not changing. But if you find the derivative, well, second derivative, at the point 0, you're going to see it is equal to 0. So even though it is 0, the second derivative was positive before and after. So the behavior of concavity did not change. So once again, be careful with this. Be careful to understand what it actually means to be inflection point. The definition was given before. So just to mention the second derivative test, but then I'm going to stop right here. What is the second derivative test now? This is just like the first derivative test. It allows you to classify critical points as either the local min or local max. But now it's using the second derivative instead of the first. Here's how it works. Technicalities, the second derivative function must be continuous. And it must apply this to a critical point. That's important. So it has to be a point where f prime is equal to 0. Or it cannot be a DNE because we're saying f double prime exists. So it is already a point where f prime is 0. Then if f double prime is positive, the point must be a local minimum. If it is negative, must be a local max. If it is 0, the test is inconclusive. You don't know. It might be a local min or max or not, or neither. We'll come back to this during recitation for more practice, but just like try to think about it for a while to convince yourself that it makes sense. So imagine a point where the derivative is 0, but such that f double prime is positive. So the function looks like a smile. That would be the first picture here. And you can see from the picture, the point must be a local minimum. Okay, it's a valley. Similarly for the second point, once again, it is a point where the derivative is 0. And the point is a local max because the function is now a frown. But if the second derivative is equal to 0, the test is inconclusive. You just can, this never tells you anything. Second derivative equal to 0 doesn't mean anything in general. But I'm gonna leave this for recitation, this problem and the last remark. Yeah, let's not do that now because we're basically out of time. So for recitation about this topic, I'm gonna recap everything and talk a little bit more in detail about the second derivative test.